US Physics Olympiad year 2021 USAPHO final round. This year all competition was held in one day. There were given 3 big problems with many questions, so it was given 5 hours for all day. If you need more interesting problems, just subscribe for this channel. Problem 1. The jet stream. The jet stream is an eastward with a current that moves over the continental United States at an altitude of 23 to 35,000 feet. The range of typical cruising altitudes of commercial airlines. This strong current affects the flight times significantly. Flights traveling eastward fly significantly faster than flights traveling westward. This problem consists of 2 independent parts. In the first part, you will consider a simple model for airplane flight. In the second part, you will determine the jet stream speed on a fictitious planet called Orb. Part 1. The power that a plane expends is used both to combat drag and to generate lift. Throughout this part of the problem, you may assume that the plane travels without horizontal velocity v-rel relative to the air. The density of air is rho air. The mass of the plane is m, and the cross-sectional area of the plane is ACS. Question A. The drag force on an airplane is given by F drag equal -1/2 CD rho air ACS multiplied by absolute value for v-rel and multiplied by vector v-rel, where CD is the drag coefficient, which depends on the shape of the plane. Write an expression for the power expended by the airplane to combat the drag force from the air. Question B. Airplanes generate lift by deflecting air downward. 1. Estimate the air mass per unit time which is deflected by the wings of the plane. 2. Estimate the power expended by the plane for lift. Question C. Estimate the speed at which an airplane flies relative to the air by minimizing the power expended by the plane. To get a numeric answer, you may use the following parameters. Mass of plane approximately 8 by 10 power 4 kilograms. Raw air is about 1 kilogram per cubic meter. CD about 10 power -2. ACS is about 100 square meters. Next, we estimate the jet stream speed using flight times. Because the jet stream speed on Earth varies greatly with the location, time of year, and climate effects such as El Niño and La Niña, you will instead consider the fictitious planet Orb, where the jet stream is eastward and uniform in the region of interest. At the end of the problem is a map of the region, whose area is much smaller than the surface area of Orb. It means you can neglect the curvature of Orb. Part 2. At cruising altitude, we assume all airplanes travel at a fixed speed v-rel relative to the air. This is not necessarily the same as your answer to Part 1 Question C, which was just a rough estimate. Additionally, we assume that flights occur in 3 stages. First, taxi and takeoff. Second, flight at cruising altitude. Third, landing and taxi, and that Stage 1 and 3 take a fixed total time t0 for every flight. Question A. Suppose a plane at a cruising altitude is traveling at an angle theta away from due east relative to the ground. What is the speed of the plane relative to the ground? Give your answer in terms of v real, theta, and vw, the speed of the jet stream relative to the Earth's surface. Question B. If the plane travels a distance d, what is the total travel time t, including taxi, takeoff, and landing? Question C. Below we present some data on airplane flights on planet Earth. Each of the flight times shown below has an independent uncertainty of delta t equal 5 minutes. From the data and the map, determine VW and VREL, giving your answer in kilometers per hour with the uncertainties. Indicate clearly what two quantities you are plotting against each other on each graph that you plot. These are data and a sheet to work with this problem. Solution for problem 1. Part 1. Question A. Solution for question A. Because we have by definition that power equal dot product by force and velocity, we have power equal 1/2 CD rho air ACS multiplied by V real in power cube. That was a solution for question A, part 1. Answer for question B. Estimate the air mass per unit time, which is deflected by the wings of the plane. Because mass flux is given by rho multiplied by V, so the rate is rho V multiplied by ACS. That was answer for question B, first one. Second one. Estimate the power expended by the plane for lift. Solution. Suppose the deflected air has a velocity u downward. Then the lift force is given by this formula mg equal rho v real multiplied by ACS multiplied by u. From here we can find what is this velocity u, and finally we have power equal Fu or m square g square over rho v real ACS. That was a solution for second part of question B. Solution for question C. Total power which we need to fly equal to sum of power against air plus power to hold the plane on vertical. So that will be sum of these two powers. The minimum power occurs when the derivative by speed equals 0. So we have dp over dv equal this expression, from which we can count v equal this expression, or approximately using these numbers that will be about 300 meters per second. That was solution for question C in part 1. Question A from part 2. Suppose a plane at cruising altitude is traveling at an angle theta away from due east relative to the ground. What is the speed of the plane relative to the ground? Give your answer in terms of v real, theta, and vw, the speed of the jet stream relative to the Earth's surface. Solution for question A. The velocity of the plane relative to the ground is v. the velocity of the plane relative to the air is v real, and the jet stream velocity vw, so that will be such picture. V it's velocity of plane relative to the ground when the angle theta to horizontal. Vw that's velocity of jet stream, and v real that's relative velocity of the plane to wind. So finally, because phi equal pi minus theta, we have from cosine theorem this expression, and changing phi to theta we have this expression. And solving it, this quadratic equation relative to v, we have this solution. Of course, we assume that v wind must be less than v real, as otherwise flying westward would not even be possible. That was a solution for question A from part 2. Question B. If the plane travels a distance d, what is the total travel time t, including taxi, takeoff and landing? Solution for question B. The answer is given by t equal d over v plus t0, where v is our answer to the part A, this one. So that was a solution for question B. Question C from part 2. Below we present some data on airplane flights on planet Earth. Each of the flight times shown below has an independent uncertainty delta theta equal 5 minutes. From the data and the map determine VW and V real, giving your answer in kilometers per hour with the uncertainties. Indicate clearly what two quantities you are plotting against each other on each graph that you plot. Solution for question C. Note that pairs of cities given in the second table are directly north-south of each other. For such cities, we expect the times in each direction to be equal up to the timing uncertainty, and the expression for the times simplifies from this expression to this expression, because theta is pi over 2 and the cosine is 0 and the sine is 1. We can read t and s of the second table and calculate d from the figure. The unknown quantity theta 0 goes into the intercept, while the slope is this one. Next, consider the pairs of cities given in the second table. We can cancel out the effect of t0 by considering the difference in flight times in the two directions. So we have t12 minus t21 equal this one, and after simplification that will be this one. Therefore, plotting the time difference versus d cosine theta, where theta can also be measured from the graph, gives combining these two results, this one and this one, we can find that v real equal 860 plus minus 50 kilometers per hour, and VW equal 370 plus minus 30 kilometers per hour. That was solution for question C, part 2. US Physics Olympiad, year 2021, USA, PHO, final round. Problem 2. The dark forest. Dark matter could be made of hypothetical extremely light particles called axions. Because individual axions are so light, experiments do not search for individual axions, but rather for the classical axion field formed by a large collection of axions, which oscillates as A as a function of t equal A0 sine omega t. This is analogous to how a large collection of photons can form a classical electromagnetic field. In the presence of a magnetic field B and an axion field A, the axion field produces an effective current J equal G A dot B, where we define A dot as first derivative from A by time d. The effective current produces electromagnetic fields in exactly the same way as ordinary current, though it does not come from the motion of actual charges. Experiments can search for axion dark matter using systems which are resonantly driven by this current. You may use fundamental constants in your answers, such as speed of light, c, h, that's a Planck constant, E, that's a charge of electron, G, that's a gravitational constant, mu0, that's magnetic permeability for vacuum, Kb, that's Boltzmann constant. You do not have to provide numeric answers unless asked. When asked to estimate, you may drop constants of order 1. The numeric values provided below are from standard references where h, c, mu0 and epsilon 0 are set to 1. To get correct numeric results, you must restore these factors yourself. Part 1. First, we will describe some physical properties of the axion field. A. Consider a single axion at rest with mass m. Find its associated angular frequency omega. This will be the angular frequency of the corresponding classical field when there are many axions. B. Suppose dark matter is distributed spherically symmetrically in the galaxy with a uniform density ρ. The solar system is a distance r from the center of the galaxy and orbits around it with a period t. Neglecting everything besides dark matter, find the dark matter density ρ. C. The energy density of the axion field is m square A0 square over 2h power 3 c. Find the axion field amplitude A0. D. The radius and the period of the Sun's orbit, as well as the typical axion mass are r equal 2.5 by 10 power 20 meters, t equal 7.1 by 10 power 15 seconds, m equal 1.0 10 power negative 9 electron volt. Numerically compute the axion field amplitude A0. E. In this problem, we treat the axion field as spatially uniform within a terrestrial laboratory. To verify that this assumption is reasonable, numerically estimate the axion field's wavelength, lambda, assuming the axions have the same galaxy speed as the Sun. F. In part A, you found omega by neglecting the axion's speed. In reality, the axion's finite speed changes the frequency to omega plus delta omega in the frame at rest with respect to the galactic center. Numerically estimate delta omega over omega to show that it is reasonable to neglect this effect. Solution for problem 2. Part 1. Question A. Consider a single axion at rest with mass m. Find its associated angular frequency omega. This will be the angular frequency of the corresponding classical field when there are many oxyons. Solution. The oxyon is a quantum particle and satisfies the de Broglie relation. Energy equal Planck constant multiplied by omega, and its energy comes from rest mass, so it is E equal mc square. So from here we can find that omega equal mc square over h. This is the answer for question A, part 1. Question B. Suppose dark matter is distributed spherically symmetrically in the galaxy with a uniform density ρ. The solar system is a distance r from the center of the galaxy and orbits around it with a period t. Neglecting everything beside dark matter, find the dark matter density ρ. Solution. Setting the centripetal acceleration equal to gravitational acceleration, we have r omega square equal g m over r square, omega equal 2 pi over period t, and mass equal 4 over 3 pi r cube ρ. So using this data, put them to this left formula and we will get this equation. From here we can count what is the density ρ. That will be ρ equal 3 pi over g t square. That was solution for question B. Question C. The energy density of the oxyon field is this expression. Find the oxyon field amplitude A0. Solution. The dark matter density comes from the mass energy of the oxyon field. So we have ρ c square equal this expression from previous condition. From here we can find that A0 equal this square root, which is answer for question C. Question D. The radius and the period of the Sun's orbit, as well as a typical oxyon mass, are r equal 2.5 by 10 power 20 meters, period t equal 7.1 by 10 power 15 seconds, and mass of oxyon equal 1.0 by 10 power negative 9 electron volts. Numerically compute the oxyon field amplitude A0. Solution. Here we can use results which we got from previous questions. So we have A0 equal this expression and ρ was this expression. Plugging in numbers and noting that provided value of the oxyon mass is really its energy, and hence dividing it by c square gives the value A0 equal this number. So that was a solution for question D. Question E. In this problem we treat the oxyon field as spatially uniform within a terrestrial laboratory. To verify that this assumption is reasonable, numerically estimate the oxyon field's wavelength lambda, assuming the oxyons have the same galactic speed as the Sun. Solution for question E. The oxyon speed is 2 pi r over period t, which is about 2 by 10 power 5 meters per second. Using the de Broglie relation again, we have lambda equal h over p, which is h over mv, and that's about 10 power 6 meters. As expected, this is much larger than the apparatus considered below. Note, a common mistake was to write v equal f multiplied by lambda, where f is frequency and lambda is wavelength. but this is only true for waves which travel at constant speed, such as light. To see the problem, note that if you applied the de Broglie relation, this equation becomes V equal energy over momentum. That's true for photons where E equal pc, but certainly not true for massive particles. Some students also tried the Compton wavelength lambda equal h over mc, but this is different quantity, namely the wavelength of a photon if it had the same energy as an oxyon at rest. So this lambda is correct solution for question E. In part F, question F. In part A, you found omega by neglecting the oxyon's speed. In reality, the oxyon's finite speed changes the frequency to omega plus delta omega in a frame at rest with respect to the galactic center. Numerically estimate delta omega over omega to show that it is reasonable to neglect this effect. Solution. Because energy E equal h omega, we need to see how the energy is changed. We have delta E over E approximately equal mv square over 2 divided by mc square, which is v square over 2c square, where we used the fact that v computed above is non-relativistic. We thus find that delta omega over omega approximately equal to 3 by 10 power negative 7, which is as small as expected. Note that usual Doppler shift formula would not work here. Trying to use it would get the wrong answer. The Doppler shift formula applies to particles with a constant speed, which satisfy omega equal vk. The oxyon is massive when at rest. It has omega not equal 0 and k equal 0. However, you could also get the answer by Lorentz transforming the 4-vector omega k. So that was solution for question F. Next, the abracadabra experiment, where abracadabra is abbreviation for this one. Currently taking data at MIT is a toroidal solenoid with the inner and outer radius r in and r out and the height h. You may assume that h much greater than r out for simplicity. A superconducting wire carrying current I wraps n times around the toroid, where n is high enough to neglect the discreteness of the wires. A circular pickup loop with a radius slightly less than r in is placed at the center of the toroid. Part 2. Now we will find the axion signal generated in the abracadabra apparatus. A. Find the magnetic field B as a function of R inside the toroid due to the superconducting current. B. The superconducting wires lose their superconductivity when exposed to a magnetic field greater than B max. Find the maximum possible current I max that can be used and assume this current is used in later parts. C. Assuming that omega is small, find the magnetic flux Fb as a function of t through the pickup loop due to the axion field in terms of A0, G, omega, B max, and the dimensions of the apparatus. You may ignore any currents induced on the surfaces of the superconducting wires. According for them makes the problem much harder, but does not substantially affect the final result. D. If omega is too large, the result above breaks down due to radiation effects. Estimate the frequency omega c where this happens. E. Using the design values R in equal 0.5 meters, R out equal 1 meter, and H equal 2 meters, estimate the numerical value of omega over omega c. F. Let F0 be the amplitude of the time-varying axion flux. Using the typical values B max equal 5.0 Tesla, G equal 1.0 by 10 power negative 16 giga electrovolts in power negative 1, and your previous results, compute the numerical value of F0. Solution for part 2. Now we will find the axion signal generated in the abracadabra apparatus. Question A. Find the magnetic field BR inside the toroid due to the superconducting current. Solution. Due to Ampere law and radial symmetry, we have magnetic field outside of this solenoid is 0, and inside integral by a circle radius at r. So we have 2 pi r b equal mu 0 and I multiplied by vector theta. And from here we can find that magnetic field equal this expression. This is a typical magnetic field inside of solenoid. Question B. The superconducting wires lose their superconductivity when exposed to a magnetic field greater than B max. Find the maximum possible current I max that can be used, and assume this current is used in later parts. Solution for question B. B max will be for R equal R in, so it means that B maximum equal this expression, and from here I maximum equal this expression. That was a solution for question B. Question C. Assuming that omega is small, find the magnetic flux Fb as a function of t through the pickup loop due to the axion field in terms of A0 G omega B max and the dimensions of the apparatus. You may ignore any currents induced on the surfaces of the superconducting wires. Accounting for them makes the problem much harder, but does not substantially affect the final result. Solution. The effective current J equal GA dot B from definition, which is equal to this expression due to previously found B equal this one and B max equal this one. So the resulting field is like that of an array of concentric solenoids where we may neglect fringe fields because H much greater than R out. Therefore the axion produced field Bx inside the pickup loop is uniform. For simplicity we define J0 equal GA0 B max omega. Then using Ampere's law we have Bx equal this integral, which is finally giving us result mu 0 J0 logarithm R out over R in multiplied by cosine omega t. The magnetic flux through the pickup loop then will be pi R in square Bax, which is equal this expression. This is the solution for question C. Question D. If omega is too large, the result above breaks down due to radiation effects. Estimate the frequency omega c where this happens. Solution. In the calculations above, we have assumed that the fields are quasi-static, neglecting the radiation propagation time. The approximation breaks down when Omega c is order of speed of light c over r in, past which the flux will be diminished. Since this calculation is approximate, the answers c over r out or c over h are also acceptable. That was a solution for question D. Question E. Using the design values r in equal 0.5 meters, r out equal 1.0 meter, and h equal 2.0 meter, estimate the numerical value of omega over omega c. Solution. Plugging numbers in, we have omega c is order of c over r in, which is 6.0 multiplied by 10 power 8 seconds power negative 1, and omega, which we found from the first part question A, that's mc square over h, and plugging numbers we have mass of oxygen, which is 1.0 multiplied by 10 power negative 9 electron volts, and h equal this one. So finally, after calculations, we will get approximately 1.5 multiplied by 10 power 6 seconds power negative 1. And from here we have omega over omega c is order of 0.0025, which is as small as expected. Any answer within an order of magnitude is acceptable. That was a solution for question E. Question F. Let F0 be the amplitude of the time varying axion flux using the typical values B max equal 5.0 Tesla, G equal 1.0 by 10 power negative 16 giga electron volts in negative power, and your previous results. Compute the numerical value for F0. Solution. From a previous question we found that magnetic flux Fb as a function of time was this expression, or F0 equal this expression. First, we have to restore the dimension of G. Notice that since current G A dot B has the same units as displacement current epsilon 0 E dot, the quantities GA and E over B multiplied by epsilon 0 must have the same dimensions, and furthermore E over B has dimensions of speed. Now in 1C we found that A has dimensions of energy times velocity, while the value of G given here has dimensions of inverse energy. Thus the combination GA only has dimensions of speed, which means a factor of epsilon 0 was left out. In other words, if we denote the value given above as G prime, the true value of G is epsilon 0 G prime. Now, using expression for J0, we can regroup expression for F0 in form of F0 equal this expression, and using that C square equal 1 over epsilon 0 mu 0, we can rewrite F0 in grouping form. And now, after regrouping and putting numbers, we have answer for F0 equal 3.3 by 10 power negative 21 Weber. That was a solution for question F. Next, the pickup loop has inductance L and is attached to a capacitor, forming a circuit with a resonant frequency equal to the axion frequency omega. The circuit also has a small internal resistance R in series and is at temperature T. The axion signal can be detected by monitoring the current in the circuit. The main source of noise is thermal noise, which causes fluctuations in the current. Part 3. We will now estimate the sensitivity of abracadabra to axions. A. The axion produces a current which oscillates sinusoidally. Find the signal current amplitude Is in terms of omega f0 and the circuit parameters. B. Find the average value of the current squared, I square, in the circuit due to thermal noise. C. At any moment in time, the noise current is oscillating sinusoidally with a typical amplitude In equals square root from mean I square, which is much larger than Is. However, the phase of the noise current also fluctuates randomly, so that after a typical time Tc, its phase will be roughly independent of the phase it had before. Find an estimate for Tc in terms of omega and the circuit parameters. Hint: at any given moment, the thermal noise current is simultaneously being produced by the random motion of electrons in the circuit and damped by the resistor. D. Suppose the experiment runs for a total time Te much greater than Tc. Roughly estimate the average amplitude of the noise current over this period of time. E. The axion is detectable if the signal current amplitude is larger than the average noise current amplitude, and the circuit parameters are L equal 1 millihenry, R equal 10 milliohm, and T equal 0.1 Kelvin. Roughly numerically estimate the time needed to potentially detect the axion. Hint: if your answer seems strange, note that in reality the axion's phase also fluctuates over time because of the effect of part 1f. In addition, we don't know omega ahead of time, so the experiment needs to be run many times. We ignored these effects here to keep things simple. Part 3. We will now estimate the sensitivity of abracadabra to axions. Question A. The axion produces a current which oscillates sinusoidally. Find the signal current amplitude Is in terms of omega f0 and the circuit parameters. Solution. Since the axion is at the resonant frequency, the impedance of the circuit is approximately R. Therefore, the current is EMF over R, which is equal -1 over R multiplied by dFB over dt. So, it means that amplitude will be omega f0 over R. That was the solution for question A. Question B. Find the average value of the current squared I square in the circuit due to thermal noise. Solution. The energy stored in the inductor is L I square over 2. By the equipartition theorem, the average energy stored in any such quadratic degree of freedom is kBt over 2. So, average for I square equal kBt over L. That was solution for question B. Question C. At any moment in time, The noise current is oscillating sinusoidally with a typical amplitude In equal mean square root from I, which is much larger than Is. However, the phase of the noise current also fluctuates randomly, so that after a typical time Tc, its phase will be roughly independent of the phase it had before. Find an estimate for Tc in terms of omega and the current parameters. Hint: at any given moment the thermal noise current is simultaneously being produced by the random motion of electrons in the circuit and damped by the resistor. Solution: the noise current that exists in the circuit at any given moment by definition came from the thermal motion of electrons in the circuit up to time Tc ago. Therefore, Tc is roughly the characteristic time for decay of current in the circuit. There are many ways to calculate this. Therefore, Tc is roughly the characteristic time for decay of current in the circuit. There are many ways to calculate this, but a simple way is to note that Tc is order of Q over omega, and Q equal omega L over R, where Q is the quality factor. Thus, Tc is order of L over R. That was a solution for question C. Question D. Suppose the experiment runs for a total time Te much greater than Tc. Roughly estimate the average amplitude of the noise current over this period of time. Solution: uncertainty goes down by square root from n when average n independent trials. Here we have n equal Te over Tc, so average amplitude is In multiplied by square root from Tc over Te. That was a solution for question D. Question E. The auxin is detectable if the signal current amplitude is larger than the average noise current amplitude, and the circuit parameters are L equal 1 millihenry, R equal 10 milliohm, and T equal 0.1 Kelvin. Roughly numerically estimate the time needed to potentially detect the auxin. Hint: if your answer seems strange, note that in reality the auxin's phase also fluctuates over time because of the effect of part 1f. In addition, we don't know omega ahead of time, so the experiment needs to be run many times. We ignored these effects here to keep things simple. Solution: by setting Is equal average In, we find that Te has order of kBTR over omega square f0 square, which is equal to 550 seconds. In reality, you would need to repeat this experiment millions of times to scan a sufficient range of omega, and the time in each step would be longer because after some point the average auxin signal also starts going down as 1 over square root from n. That was solution for question E part 3, and here we finish discussion for whole problem 2. US Physics Olympiad, year 2021, USAPHO, final round. Problem number 3. Great Hall. The classical Hall effect was first measured by Edwin Hall in 1879, shortly after the publication of Maxwell's equations. In all parts of this problem, materials contains NV electrons per unit volume, and each electron has charge QE less than 0 and mass ME. You may use these quantities in all of your answers. We will begin by investigating the implications of the classical Hall effect. Part 1. An infinite plate in the XY plane with a thickness d in the z direction is placed in a uniform magnetic field B equal B multiplied by unit vector z as shown. An electric field E equal E multiplied by unit vector x is applied in the plane of the plate and the system is allowed to reach a steady state. Question A. If the electrons have velocity v at steady state, what is the current density J? Recall that J is defined as the total flow of a charge through a unit cross-section area per unit time. Question B. In the Drude model, electrons are subject to both the Lorentz force and damping force negative gamma v, where gamma is a constant that depends on the material. In the above system, what is the current density in the steady state? Give both the magnitude and the direction of J in polar coordinates. Question C. Compute the electrical resistivity ρ0 equal limit for B going to 0 for relation E over absolute value Jx, and the transverse Hall resistivity ρh equal limit for gamma going to 0 for relation E over absolute value Jy. Question D. A Hall effect sensor detects the strength of magnetic fields. Consider the following circuit consisting of a square plate of side length L and thickness D in a perpendicular uniform magnetic field B. A longitudinal EMF E is applied to the plate. At steady state, a Hall voltage VH is measured across the plate due to the buildup of a charge in either side of the plate. If the electrical resistivity of the plate at zero magnetic field is ρ0, what is the Hall voltage VH and the current I through the plate? Express your answer in terms of ρ0, E, B and the dimensions of the plate. Solution for problem number 3. Question A. If the electrons have velocity v at a steady state, what is the current density J? Recall that J is defined as the total flow of a charge through a unit cross-sectional area per unit time. Solution. If there are nv electrons per unit volume and they have a velocity v at a steady state, then nv multiplied by v will be number of electrons crossing unit cross-sectional area per unit time, and the current density is given by nv QE multiplied by V. That was solution for question A. Question B. In the Drude model, electrons are subject to both Lorentz force and the damping force negative gamma V, where gamma is a constant that depends on the material. In the above system, what is the current density in the steady state? Give both the magnitude and direction of J in polar coordinates. Solution. The equation of motion for an electron in vector form is this one, which gives us a system of two equations with two unknowns. To simplify this system, we can write that Vy equal this one through Vx, and Vx equal this one. Finally, we can get Vx and Vy. That will be this one. Now, expressing J through V, we can find that Jx equal this one and Jy equal this one. Then, as I requested, we can compute the magnitude and the direction. In polar coordinates, that will be this one. This is magnitude, this is angle theta. So that was a solution for question B. Question C. Compute the electrical resistivity ρ0 equal limit for B going to 0 for E over absolute value Jx, and the transverse Hall resistivity ρh equal limit for gamma going to 0 E over absolute value Jy. Solution. Using a result in question B, we can write that Jx equal this one and Jy equal this one. And from here we immediately can get result. ρ0 equal gamma over NV multiplied by QE square, and ρh equal B over NV QE. That was solution for question C. Question D. How effect sensor detects the strength of magnetic fields? Consider the following circuit consisting of a square plate of side length L and thickness D in a perpendicular uniform magnetic field B. A longitudinal EMF E is applied to the plate. At steady state, a Hall voltage VH is measured across the plate due to the buildup of charge on either side of the plate. If the electrical resistivity of the plate at zero magnetic field is ρ0, what is the Hall voltage VH and the current I through the plate? Express your answer in terms of ρ0, E, B, and the dimensions of the plate. Solution. The Hall voltage is such that the electric field from the external EMF and from the charge build-up cause the current to flow in the x direction. Our equation of motion is this one. Thus, we have VH equal LVXB and LVX equal QE multiplied by EMF and divided by gamma. Remember that we counted what is ρ0 in previous. That was this expression from which we can find what is gamma using ρ0. Now we have enough information. Substantiating gamma, we have for VH this expression, and for current I, by definition this one, or after calculation ED over ρ0. That was solution for question D, and we finished with the part 1. Experiments in the 20th century revealed that in many materials the Hall resistivity could only take certain discrete values. We will now show how this follows from Bohr quantization. These next parts are independent of the first part of the problem. Part 2. A zero resistance loop of wire of radius r and the cross-sectional area AW carries counterclockwise current I. Solenoid through the middle of the loops carries magnetic flux F out of the page, which we define to be the positive Z direction. Question A. If the electrons all have the same speed, what is the angular momentum of each electron? Question B. If we allow the flux in the solenoid to change, the usual mechanical angular momentum L of each electron is not conserved. Instead, quantity called the canonical angular momentum L can equal L plus C QEF for some constant C is conserved. Find C. Question C. The Bohr quantization condition says that for a closed circular orbit an integer number of the de Broglie wavelengths must fit in the circumference. The de Broglie wavelength is lambda equal h over p can, where h is Planck's constant and the p can equal L can over r is the canonical momentum. For a given solenoid flux F, what is the set of allowed mechanical angular momenta L? Question D. What is the momentum possible change in the magnetic flux for which the same set of mechanical angular momenta is allowed? This is known as a flux quantum. Part 2. A zero resistance loop of wire of radius r and cross-sectional area AW carries a counterclockwise current I. A solenoid through the middle of the loops carries magnetic flux F out of the page, which we define to be the positive z direction. Question A. If the electrons all have the same speed, what is the angular momentum of each electron? Solution. The current is charge of electron multiplied by electron concentration multiplied by speed and multiplied by cross-sectional area. From here we can find that speed equals this expression, and using definition for angular momentum we have L electron equal mass of electron multiplied by speed by radius, which is this value. That was solution for question A. Question B. If we allow the flux in the solenoid to change, the usual mechanical angular momentum L of each electron is not conserved. Instead, a quantity called the canonical angular momentum L can equal L plus C QEF for some constant C is conserved. Find C. Solution. We compute the change in angular momentum associated with a change in flux delta F. By Faraday's law, there is an induced electric field resulting from the change in magnetic flux, which is EMF equal 2 pi r E equal negative dF over dt, where E is induced electric field. The electric field results in force mass of electron multiplied by dV over dt, which is equal QE multiplied by electric field. So using expression for electric field, we can find that change of speed proportional to change of magnetic flux. So it means that rate of change of angular momentum equal negative Q over 2 pi multiplied by delta F over delta T. Therefore, change of angular momentum equal negative Q over 2 pi multiplied by change of magnetic flux. Then for L plus C QF to be conserved, C must be equal 1 over 2 pi. That was solution for question B. Question C. The Bohr quantization says that for a closed circular orbit, an integer number of de Broglie wavelengths must fit in its circumference. The de Broglie wavelength is lambda equal h over p can, where h is Planck's constant and the p can equal L can over r is the canonical momentum. For a given solenoid flux F, what is the set of allowed mechanical angular momenta L? Solution. The circumference of such an orbit is 2 pi r. A de Broglie wavelength is given by h over p can or hr over l can. Then n 2 pi r over lambda, and finally that's equal to l can over h, where h is Planck constant over 2 pi. So we have L can equal nh, and then the allowed mechanical momenta satisfy this equation, where n is an integer. That was solution for question C. Question D. What is the minimum possible change in the magnetic flux for which the same set of mechanical angular momenta is allowed? This is known as the flux quantum. Solution. We require from previous that Q multiplied by delta F over 2 pi equal H. So it means that delta F must be equal H over absolute value charge of electron. Note that for a superconducting ring the flux quantum is H over 2QE, because the electrons come in Cooper pairs, but this wasn't part of this problem. So that was solution for problem D. Part 3. Now consider an annulus held perpendicular to a fixed uniform external magnetic field B, and suppose an additional tunable magnetic flux F threads the center of the annulus, with the both pointing out of the page. The annulus has a transverse Hall resistance RH, and EMF of E around the annulus generates a perpendicular current E over RH via Hall effect, and you may neglect its self-inductance. Question A. Suppose F begins to increase slowly and steadily in time. After a short time, the electrons will begin flowing steadily from one side of the annulus to the other. Do the electrons move inward or outward? Justify your answer. Question B. If the threaded flux increases by delta F, how many electrons pass from one end of the annulus to the other? You may use RH among other variables in your answer. Question C. As we show it in 2D, if the magnetic flux changes by the flux quantum FQ, the allowed orbits from Bohr quantization are unchanged. Quantum mechanics thus tell us that in conventional materials, if the magnetic flux changes by FQ, an integer number k of the electrons must pass from one edge to another. What constraint does this place of the Hall resistance? Part 3. Now consider an annulus held perpendicular to a fixed uniform external magnetic field B, and suppose an additional tunable magnetic flux F threads the center of the annulus, with both pointing out of the page. The annulus has a transverse Hall resistance RH, and EMF of E around the annulus generates a perpendicular current E over RH via the Hall effect, and you may neglect its self-inductance. Question A. Suppose F begins to increase slowly and steadily in time. After a short time, the electrons will begin flowing steadily from one side of the annulus to the other. Do the electrons move inward or outward? Justify your answer. Solution. The increasing flux induces a clockwise EMF. The Lorentz force on an electron is this one. Then cross product V by B must oppose E. Therefore, V must point radially inward by the right-hand rule. Therefore, electrons must be flowing radially inward. That was solution for question A. Question B. If the threaded flux increases by delta F, how many electrons pass from one edge of the annulus to the other? You may use RH among other variables in your answer. Solution. We have current equal 1 over RH multiplied by absolute value delta F over delta T. It means that total charge equal change of total flux over RH. It means that number of electrons will be delta F over RH multiplied by charge of electron. That was solution for question B. Question C. As we show it in part 2 question D, if the magnetic flux changes by the flux quantum Fq, the allowed orbits from Bohr quantization are unchanged. Quantum mechanics thus tells us that in conventional materials, if the magnetic flux changes by Fq, an integer number k of electrons must pass from one edge to another. What constraint does this place on the Hall resistance? Solution. In question B, we found that number of electrons equal this expression. So if we set k equal NE, we have QE multiplied by k equal delta F over RH. But from part 2 question D, we found that delta F must be equal to H over QE. Combining these two equations, we have RH equal H over K Q square. This is known as the integer quantum Hall effect, and it applies to any material shape. So that was solution for question C from part 3. We did all questions for part 3, and now we finished all problem number 3 from year 2021.